did all those last chapter. The Pythagorean identities, that actually was in last chapter, but we didn't do it at all. So you should already know this one from last year. The sine squared of x plus the cosine squared of x equals 1. Yes? Okay, so that sounds familiar. Did you do these two last year? 1 plus tangent squared is secant squared. No. Okay. So these two, you also have to know, memorize, and be able to use. But I'm going to give you some good, helpful, because, again, the less you have to memorize, in my opinion, the better. So here's why you can avoid memorizing those two, and you can kind of derive them on your own. As long as you have this one memorized, and I assume most of you do because you've been doing this for the past 2 years, if you divide everything in here by sine squared, you don't need to write this unless you want to. But if you divide everything by sine squared divided by sine squared is 1. Cosine squared divided by sine squared is cotangent squared. And 1 divided by sine squared is cosecant squared. So it turns into that one if you just divide everything by sine squared. Does that make sense? And similarly, if we divide everything by cosine squared, sine squared divided by cosine squared gives you this tangent squared, plus cosine squared divided by cosine squared gives you 1, and 1 divided by cosine squared gives you secant squared. So they are, in a way, they're all the same thing. They all definitely come from the same basic Pythagorean identity. It's just you might be presented with a 1 plus tangent squared, and you can take that out and replace it with a secant squared. So what I would probably do at like the top of a test or something, or anywhere, once an identity comes up and you feel like there's maybe some potential to use it, is I would write that at the top, and then I would derive these other two. Okay? Also, we're going to be using different arrangements of this. So, for example, if you see a 1 minus cosine squared, that's just a rearranged version of this one, right? If I subtract cosine squared over, 1 minus cosine squared will equal sine squared. So if I ever see a 1 minus cosine squared, I'm going to potentially replace it with a sine squared. So you can use any rearrangement of these, which is also why it's helpful to visually have them down so you can picture, like, if I have to subtract something over and so on. So that's it for the Pythagorean identities, and we'll hopefully use some of those today. And then even and odd stuff we did last chapter, so I threw that at the top here too. So sine is odd, which means cosecant is odd. Cosine is even, which means secant is even. And tangent is also odd, which means cotangent is odd. Okay? All right, so did you do stuff like this last year, where you essentially had to prove? Yes or no? Verifying means prove that this is equal. No? It looks like that's a no. Looks like at the very least you don't remember it all, which means I'm just going to start from scratch. Okay? So, proving means that you simplify the left, simplify the right, and pray that they equal each other. Okay? I would warn you in these, I wouldn't kind of partially simplify. I wouldn't do that. I would stick to one side, complete it first, as far as you can simplify it, and then go to the other side. Because if you have too many moving parts, they may miss each other. So what I mean by that is just focusing on this side, just using any of your reciprocal function facts, your Pythagorean identities, or your even and odd stuff, simplify this. So what is secant the same as? One over cosine, so I'd change that to a 1 over cosine. What is cotangent the same as? Okay, there's two directions we could go with this. 1 over tangent or cosine over sine. I'm going to say cosine over sine, and you may have to play around with both of them. And the more you do of these, the better more fluent and quicker, you'll just kind of know without being able to really explain how you know. But I can kind of foresee that the cosine over sine is better because what cancels? Cosine x and cosine x, which leaves 1 over sine x. Now, I could call that simplified and just go to the other side, or I could keep going with that. 1 over sine x is the same as cosecant x, right? So I could just say cosecant x equals, and then in that case, I didn't really have to touch the right-hand side. So that's one way that that could be presented. If you didn't make that a cosecant x and you stopped at 1 over sine x, cosecant x is the same as 1 over sine x, and it could be left like that. Either is fine. Regardless of which way you do it, the left side has to be an exact match for the right side, and you check it off. You have to show every single step. So what we changed secant to, what we changed cotangent to, what canceled, what that became, and then what that became. You can't skip steps. Okay? And when they become more complicated, you'll hear me push you to only like do 1 or 2 things. Don't change 8 things at once. Change it, and that's a new line, because the biggest thing with proofs is you're trying to communicate how this all works out. So if I can't follow what work you're doing because you're jamming 8 steps into one, you're going to get points off. If I can't follow, because that is the goal of proving, is to spell it out for a reader so that they can follow and understand how this all transpired. Okie doke? And the biggest thing is people see it, but they're too lazy to write it all down, so your communication suffers and it's not as clear, and you lose points. Okay? Example 2, if I'm just focusing on the left side first, what would you maybe try to change about that? Morgan, come up with something. Let's change tangent to sine over cosine, so sine of x I'll leave. Tangent will become sine of x over cosine of x plus cosine of x. Okay, Olivia, what would you then do with that? Yep, so that would be sine squared x over cosine x plus cosine x. If I want to continue simplifying the left-hand side, if I want to actually do the addition, what do I need in order to add these 2 terms? I need a common denominator, right? A fraction with a non-fraction. So I would put this over 1, and this needs a what to be the same as this side? What do I multiply this by? Mitch. Cosine x over cosine x to get a common denominator. So that's going to change it into sine squared x plus cosine squared x all over cosine x. Sorry, I didn't make this long enough. We're going to have to, if that happens to you, try to just be clear about where you're going next. Because I'll assume that you're working down. That is the way proof should be written. Step by step by step, working vertically. And then if you did run out of space, you could just jump it over. So what can I now change about this? Bailey? That's a 1. So I'm going to make this 1 over cosine x. And then I cancel equals 1 over cosine x. And then 1 over cosine x is what, Connor? Secant x. Now this is a little weird because I haven't even started the right-hand side, and that's because I'm not going to do anything to it. That equals secant x. Check. I really have to touch the right side. Okay, so simplifying, a lot of times is changing things into sines and cosines, so stuff cancels. Can be having to get a common denominator in order to add things together, and then an identity pops up. You know, you don't really know what's going to eventually pop up. You just have to be ready and willing to use all these tools. How about this last one? What do you think you would try first? And there may be a lot of trial and error in this until we get comfortable. The more complicated side is the left side, so I would say, what might you do to that first? Krista? You could factor out a cosine. Exactly. If you factor out a cosine x, you're left with 1 minus sine squared x. What could you do with that? Do you see anything with that? Andrew? 1 minus sine squared. If you see sine squareds and cosine squareds paired with 1s, you're almost always going to be pulling your identities into it. So 1 minus sine squared x isn't the exact version of that, but if I subtract a sine squared over from both sides, I will see that cosine squared is equivalent to 1 minus sine squared, yes? So this 1 minus sine squared can now be turned into a cosine squared. And then cosine times cosine squared is cosine cubed. And again, I don't have to touch the right-hand side. It's done. Okay? Can I show you just another option? Just so you guys don't feel pigeonholed like there's one and only one way. Especially if you look at your answers in your back of the book. That's just going to show you one of potentially a gazillion methods. So if I were to start this one over again, and again, all of your gut instincts might be different, and some will be easier than others, no doubt, but they're all doable. If you see sine squared, and you want to replace that, just that, with 1 minus cosine squared, right? Can we all agree that if I subtract cosine squared over, sine squared will equal 1 minus cosine squared? So I could substitute that out. And then distribute, which would leave me with cosine x minus a cosine x, plus, because a negative times a negative, cosine cubed. And then if you combine like terms, cosine x minus cosine x cancels, and you have cosine cubed x equals cosine cubed x. Done totally differently. But just, do you remember in geometry, proofs could be done in many different ways. Some of them are very straightforward, and there's just definitely a dominant way. And sometimes there's only one way, but sometimes you have lots of options. And the more complicated they get, just like proofs in geometry, the more variations there probably are. So stick with it. If you go down a path and it doesn't seem to be panning out for you, you can start over and just start a different avenue. Okay? All right. Oh, these are all proofs. This is fun. Okay. On this one, I'm probably gonna show you this in 2 different ways too. I want to show you something that you can do. If I forced your hand and I said, well, what can you change the left side to? What would you do? How could you rewrite that left side into an equivalent expression? Joey, do you know? Right. You have a binomial that's being divided by cosine. So each term can be divided by cosine separately. So 1 over the cosine of theta plus sine theta over the cosine of theta. And if you do that, then 1 over cosine is secant theta, and sine over cosine is tangent theta, and you're done. And that's your properly written proof. But some of you would definitely look at that original proof, and you might be more tempted to work on the right-hand side first, because the left side is already in terms of sine and cosine. So you might be tempted to make your secant 1 over cosine, and your tangent sine over cosine, and add the fractions. You don't need to get a common denominator because that's already done for you, but when you add the fractions, you're done. So, 2 totally different ways of doing it. Your final statements are totally different, but they're both good proofs. One just worked on the left side completely, the other one just worked on the right side completely. Okay, exercise 5. Bridget, give me something to try first. Okay, so what does this one need? Cosine of x. And what does this one need? Okay, so this one's going to become cosine squared x plus this is going to be, you got to kind of FOIL, right? 1 times 1 is 1. Plus a sine x on the outer and plus a sine x on the inner is going to be plus 2 sine x plus sine squared x. Your fluency with that is going to depend on your fluency for squaring a binomial, right? So if you really need to take the time to write it side by side, I would encourage you to do that. Don't try to take shortcuts you're not comfortable making. So 1 times 1 is 1. 1 times sine x is sine x. 1 times sine x is another sine x. Sine x times sine x is sine squared. Combine like terms, and that's what you have. And it's all over your common denominator of cosine x, 1 plus sine x. Okay? Now what can we do with that side? Marissa, what do you see on that left side that you could clean up? Say that one more time. Okay, so yes, so this identity tells us that that plus that is 1. So we'll have 1 plus 2 sine x. And I think the most obvious transition there is just to combine like terms. So 2 plus 2 sine x. Nate, what could you do next to this left-hand side to continue simplifying? How about your numerator? How could you rewrite your numerator? Say that again. 2 plus 2 sine x, and then what? Well, I'm looking for you to rewrite the numerator into an expression that doesn't look like 2 plus 2 sine x. Yes. You can factor out a 2. I'm going this way, by the way. And do you see what that did for you, Nate? What? Right, 1 plus sine x cancel. So I have 2 over cosine x. Oh, I'm running really out of room. I'm going to go because I don't want to run into number 6. So 2 over cosine x is like the same as 2 times 1 over cosine. right? And 1 over cosine is secant. So it's 2 secant x equals, and your right side was always 2 secant x. Let me give myself a little border. Obviously on your homework, you're on a separate sheet of paper. You can work down the entire time. Okay. Critically important for exercise 6 here. You cannot cross multiply. Okay? Cross multiplying is something that you're allowed to do if you know that two sides are equal and you're trying to solve. We don't know if these two sides are equal or not because we're trying to prove that they are. So you can't assume that they are and cross multiply. It's just one of the finicky rules of proofs. You cannot ever add 5 to both sides, for instance, because when you add 5 to both sides, you're assuming they're equal already, and saying, okay, if I start as being equal and then I add 5 to both sides, they're still going to be equal. If you're proving things, you cannot do that. You can't do things to both sides like you do when you're solving an equation that you already know is equal. So, we need to just manipulate each side. So, thoughts. What could we do here? Why don't we do this with this one? People are going to put themselves out there. Take a couple minutes and try some things. So just take a few minutes, try some things on your own. Okay. So let's see if we can sift through what, and this would be me reading it. Gosh, that board's awfully dirty, huh? So, this person multiplied the left by sine x over sine x, became sine squared, and they distributed it on the bottom. So, oh no, they didn't distribute it on the bottom. So then sine squared, and it just kind of stayed the same. And then they just divided, then they just recanceled the sine x. So they really didn't do anything to the left side after that was all said and done. Do you see that? But maybe that's because they realized something over here. So, what a good note taker. No cross multiplying. On this side, they multiplied by 1 plus cosine x over 1 plus cosine x. The numerator foiled out and became 1 minus cosine squared x over the sine x times 1 plus cosine x. 1 minus cosine squared is a Pythagorean identity, became sine squared. And then there's sine squared x and sine x reduced to just a sine x up top. Who was this? Beautiful. Nice job. So the question everyone's going to probably have is, how did you know to do that? What made you think to do that? Okay, so even though you're working on the sides separately, you can still get common denominators. So this side, to get it looking like that side, would need a sine x over sine x. And this side, to get it looking like their left side, would need 1 plus cosine over 1 plus cosine. Brilliant. Good. Okay. This person did sort of looks like the same thing. Sine x over sine x. 1 plus cosine over 1 plus cosine. They did. They did the exact same thing. They didn't re-simplify the sine squared over sine. But that's okay. They still, both sides equal each other. Yes? Any questions on that? Who was this? Good. So plus 2. So this one, Bailey, can you send that over? Mackenzie, so it gets on its way. This person split up the right-hand side, and I don't blame them for trying that, because when you have a binomial up top and you're dividing, you can split it up. But they quickly got to a dead end, because then what? Right? Was this you? Oh, this is you. So yeah, so unfortunately, you tried it, because that is a strategy we've used, but it didn't pan out. So you'd have to go back and try something else. You cannot split up the left side when the binomial's on the denominator, by the way. Not that she did, but I know some people will try. And then, Bailey, one more. Oh boy. Whose is this? This is you. Where'd this come from? Oh, this is John. Where'd that come from? The reference sheet? Where's my reference sheet? Sine x over, oh, not a bad, look at you little problem solver. He looked at his reference sheet, and the sine of something over 1 plus the cosine of something is the tangent of something over 2, and then 1 minus the cosine of something over the sine of something is tan over x. Works. Now, obviously I'm not going to have you call on stuff from this review sheet if I haven't taught it to you yet. So that wasn't the idea. And actually, if something like that was on a test, I would say to you, you cannot use this. Like, you can't use your reference sheet formulas. Because what I want you to do is kind of get the common denominator, that method. So I would tell you can't do that because that's too easy, but good job. Sorry you don't get bonus points. You didn't put yourself out there. And then, here we go. This is you, Abby. So, yep. She broke it up, and you actually took it one step further than Bridget did. You, changed 1 over sine to cosecant and cosine over, but it still didn't really pan out. So, anyway. Now we know. Okay? Send that back. On the last two, this one is going to capitalize on the fact that sine is odd. So the sine of negative x, because it's odd, turns into the negative sine of x, yes? And because there's already a minus there, it's going to be minus the negative sine of x, so it's going to be the tan of x plus the sine of x over 1 plus cosine x. Now what? Any ideas? Andrew? Right, sometimes it's helpful to get all things in terms of sine and cosine, and although that seems more complicated at first, if I make the tangent of x, sine of x over cosine x, I can then clear the complex fraction, right? What would I multiply the numerator by and the denominator by to clear the complex fraction? What's the only mini denominator in the whole problem? Cosine x. So if I multiply by cosine x over cosine x, that's going to change the numerator to the cosine x will cancel, so it'll be sine x plus sine x cosine x over I don't want to distribute this because I'm starting to see already in the numerator, what can I take out? Joy? Sine of x. So if I take out a sine of x, 1 plus cosine x will be left on the bottom, still keeping it the same. So my 1 plus cosine x's cancel, sine over cosine, tangent. So between factoring, adding fractions, clearing complex fractions, reciprocal functions, all this Pythagorean identity stuff, you've got to be creative. You've got to try new things, be adventurous. Sometimes you'll do a lot of work and you'll have to erase it. That stinks, but it's a part of the learning process. And iron these out. Okay? We don't have time for the last one, but if I'm looking at it quickly, my guess is get a common denominator between the two fractions, combine the two fractions, and I think something will probably just come out of that. Okay? So, oh yeah, I can hand them back, but I'm not going to go over them at all, but I'll hand them back. I'll give half to Bailey to hand back. These were out of 70, just so you know. So you can calculate your grade. Out of 70. Each multiple choice was minus